So I can't say that I'm going to teach you how to do basic asynchronous code in my demo. So I apologize. I'm not sure I can live up to Ravi's standard. But what I can do is give you a window into what it's like to host a really, really big group of websites, because that is precisely what we do at Sinclair Broadcast Group. So, first off, can I get everybody at least who's willing, to stand for me? All right, we're going to go through an informal survey real fast, okay? How many of you guys work at software companies? If you don't work at a software company, please sit. Okay. How many of you all have websites? If you don't have a website, please sit. Okay, good, because nobody sat down, because otherwise I was going to tell you to leave and go make a website, because it is the 21st century now. Next question. How many of you have more than 10 pages? Sit if you don't. Sit if you have less than 100 pages. Sit if you have less than 10,000 pages. Okay. Anybody still standing? No, we got a couple still. Less than 1 million? Okay. So you should be listening to everything that I'm talking about. Okay? Sinclair, in our entire universe, has 17 million pages that we support. 192 websites. 193 if you count sinclairdigital.com. We like to. This is me. Sinclairdigital.com. You can all go there and you can see jobs we've got open. You can see about who we are and what we do. And this is what I'm going to talk about today. It's a very generic slide. I'm going to go through some background information, talk about the problem of having 17 million websites to monitor, talk a little bit about the architecture that we use to monitor that group, and some of the lessons that we learned trying to monitor all of this stuff, first without Redis and then with Redis. So, as I was saying, Sinclair Broadcast Group, we've got 193 news stations. Now, that means, collectively, that we publish one new piece of information every minute of every year. Anyone know how many minutes there are in a year? Anybody? No Rent fans out there. 525,600. Yeah, for us, that's 525,600 pages. Doesn't work on a non-musical crowd, apparently. The critical bit is that we have a system wherein any one of those publishes can go to up to 600 different locations throughout our content network. That includes front pages, that includes section pages, that includes different story pages for different websites. Be that Como News in Seattle here, or be that WJLA back in Baltimore. One publish can put content on up to 600 locations. Now, the average story has 3, but up to 600 from one user action. And most critically, in the news business, if you are not the first one visible to the audience, and that includes all of your caching, it includes all of your refresh times, it includes Google. If you're not the first to the audience, you don't get the money. Our entire task as Sinclair Digital is to make sure that Sinclair can beat CNN. If we publish at the same time as CNN, we beat them by 47 seconds. That means we make money on a viral story and they don't. When Dale Earnhardt Jr.'s plane crashed, we broke that story. A CNN reporter reported it. It went on the AP, and our reporter picked it up and published it before it was live on CNN. That means we broke that story. We tripled our revenue for 4 days on one story. Now imagine you do that 50 times. You do that 100 times. You do that across a year. The more often we discover those stories, the faster we publish, the more money we make. Trouble is, we don't always know, or at least we didn't always know, when those publishes were failing. We stopped meeting that SLA, we stopped making money. So the question is, how do you monitor 17 million pages. How do you keep track of 600 possible updates for every single user action? For us, the answer to that is first, you've got to figure out how to monitor one of them. Every change has to be visible to an audience, so we started there. We started with one change to one audience member. Think about it as a burst, okay? But there are two problems we have to solve. One of them is, are we meeting that SLA? The other one is, should this piece of content be bigger? Should it be syndicated to 600? Should it go across the entire network? Is this a world-changing event? Did Trump just bomb Iran? Literally, that was a fire drill for us to make sure that it went to every single page we had, because it's world-changing news. And when you're living at the pace of news, it doesn't matter if it's 11 p.m. or if it's 2 a.m. or if it's noon. We publish once every 15 seconds. Once every 15 seconds across our network, 4 times a minute. That's not just updates, that's publishes. We have to deal with end tiers. We have to deal with CDNs. We have to deal with different systems trying to keep up with each other with a publishing timeline that has to constantly enrich this data. We have to alert when these things happen, so all of this data has to be durable. We have to put it into a system that is actually worth holding on to and that doesn't have a huge overhead, because 17 million updates every time we change a story page is not a tenable solution. So what we tried to do is to build a monitor. The monitor, from an audience viewpoint, can't be a cache breaker. It has to look at things the way our audience does. It has to have nothing special about it. It's got to act as if it's an audience member, which means we can't make it break cache. We're not trying to say, did we try to publish? We're trying to say, did we accomplish it? Did our audiences actually receive the content we produced? We're not trying to change the way a render happens so that the render isn't any faster for us than it is for anybody else. And we have to include the cache timeouts. We want 3 tiers of caches to all have to expire within that 60-second window, no matter how much is going on the system. Now, the beauty of this is that in a real world, one publish every 15 seconds is only about 3,000 pages a day. One publish every 15 seconds with an average syndication level, call it, of 3 gives us 10,000 active pages at any given time. 10,000 active pages all have to be visited within every 30 seconds. Now, anyone here familiar with the Nyquist sampling theorem? Good. Teach you a little signal theory. Turns out if you want to measure something at 1-minute intervals, you actually have to measure it at 30-second intervals. Because if you have a 1-minute gap, that means that you could miss 2 events. So you have to sample halfway so you never miss 2 events. Now, this applies to all sorts of things in monitoring, but it's a great thing to keep in mind. You want to measure a phenomenon that is a particular length, you always have to measure twice that often, twice or more. So for us, that meant that roughly 4 to 5 times a minute, we have to hit all of our systems. That's a big distributed load. No single node can do 10,000 pages every 30 seconds. It's not worth trying, really. So how do you coordinate some number of different monitors? For us, that answer was Redis. Now, you could shard and you could try and break up the space in a reasonable way, but producers aren't reasonable people. They don't plan their story names according to any kind of a pattern. You can't guess where they're going to be. Different sites have different publishing frequencies. Different producers have different publishing frequencies. Splitting up the data wasn't worth trying to do. So what we did is say, well, what if all of our monitors just share the same information? Okay? So what we ended up with is what is actually a very, very simple architecture. Take any one of our websites. This is comonews.com for any of you locals. That's channel 4 here in Seattle. comonews.com, you put a monitor on Como News and some other number of different pages. all right? And the monitor doesn't care what things it's supposed to be monitoring. It just goes through a list and it monitors all of them as quickly as it can. We start them all at a random place, and that way they all cover everybody. Any monitor goes down, we just start another one. We don't really care whether it succeeded or failed or what group it got through. We just scale up the monitors as many we need to cover all of our pages every 30 seconds. All of them calculate an MD5 hash of those front pages. That hash changes when even one bit on the screen changes. So now we know when an update happened. Every time an update happened, this monitor figures out which story or stories are new based on that Redis cached entry, puts it through what I'm calling the Redis bridge, and that's what my demo is going to be here in a second, to any kind of a monitoring system. Any kind of a monitoring system, all right? So in this case, we're going to use Kafka. I don't know if anyone's familiar with Kafka, but what we're using is Redis as a data store for decisions that are then going to be federated out through Kafka. I know this is a Redis talk, but we're going to do more technologies than just Redis. So we've got a quick demo here, and it's pretty simple, actually. The question for everybody is, can you figure out what's going on? All right. So now, I've got a service, a single monitor right now, that is running against every single one of our websites, all 193 of those websites. Every time one of our producers hits the publish button, we take that story, we composite it into our pages, we do a pre-render cycle to optimize for Google, and then we make that page public. We don't tell anyone that we made it public. I mean, we make it available in feeds, but we're not telling anybody ahead of time. There's no proactive feed telling our monitor what to look at. But every 15 seconds or so, a new story is going to be published. Every time a producer hits that publish button, a new story goes live. And you can watch this endlessly. I usually leave it up on a monitor sitting at my desk because I love to watch news come in. And it also tells me if there's anything wrong with my system. What we have right here, and I don't want to belabor this too much, but this monitors the core use case of my entire business. Anytime this stops working, anytime I stop getting stories, anytime my publishing interval stops working, I know that I'm losing money. Now I can supply that same information elsewhere. I can say, did I try to publish this minute? Did I try to publish it within a minute? I can ask, should there have been a publish this minute? I can monitor whether this system is behaving. But this tells me for real. This gives me that visceral impression that my system works. And every time one of these goes up, you should hear that cashier ring. That, I don't know, a bunch of the old timers, I'm sure, remember the sound of a cash drawer. They hit the button and suddenly everything rings. Every time one of these goes live, it's money. It is the next possible viral story, the next $100,000 worth of revenue, every time this thing pops up. Now you might ask, this is a website. How does it get Redis? Get to that after we go into how many of these we have to stand up. Okay, so that's the demo. But the question is, how many of these things do we actually need? I keep saying we have 17 million pages. We have 10,000 active pages at any given time. Well, so for any of you math nerds, this is how you figure it out. You take the number of updates, you figure out how many things you can visit in 30 seconds, and you scale until you hit the right number. Now, it's actually simpler than that. All you have to do is scale until you're catching everything. Scale until every one of your stories is caught on your system. Because no story is going to get caught twice, you know that. You've got Redis cache, it's shared. I've got 40 different services. They share a cache. None of them's going to try and hit the same thing twice. And if they do, they're going to put it onto the same Kafka topic, and my consumer's only going to consume it once because it has a Redis cache of its own. I've got a completely deliver once system because all I needed to do was tell one service to do it 100 times. As long as I randomize start position, I have as many different observers as I need. Scale them up. Don't worry about asynchrony. Don't worry about orchestration. Don't worry about trying to coordinate. Just have them write, and have them write in an immutable way. Let the asynchrony figure itself out on the other end. Works for a lot of monitoring problems. Who cares if I say it's 50 degrees outside twice? Does that hurt anyone? I don't think so. But a bigger point here is that what I just demonstrated is a unified view for our national producers. At Sinclair Broadcast Group, like a lot of places, we have a national news desk. Think of it like CNN's national news desk, ABC's national news desk. We have people, it's a group of 12, who do nothing except scroll through all of those front pages, and they do it all day long. Check a front page, go to the next one. Check a front page, go to the next one. They've got 56, something like that, different tabs up, and they just each go through all the front pages over and over and over again all day. Every time they find a story they think is of national interest, they pull it up, they edit it, they republish it, they syndicate it. Now, our system makes syndication easy, but finding it? Without this, they are scrolling through 50 pages. With this, they're watching one feed. One feed on one big monitor, and you can see every piece of news published by my entire company. 3,000 news producers, all working independently. One source of truth. Now, this is great when it stays up, which is why we went from what is currently an embedded Redis system to Redis Labs, because managed systems are wonderful. Lessons we learned, and that's sort of the gateway here. The more time you have to spend solving these problems and designing these systems, the more it makes sense to invest in someone else doing all that for you, which is why, again, self-hosted, the amount of work we had to do to get scaling right, to get different variations right, just didn't suit our problem space. We aren't going to leverage Redis to the hilt. We need a reliable data store. We need it to store information durably and distribute it. Managed makes a lot of sense for us. Redis, originally we were looking at it as a cache. We were just going to store the whole page in Redis, and we were going to check that every time. It turned out that doing that meant that only one of our monitors could ever really know whether that was coherent data. So instead what we decided to do was to store a map. Basically a map by URL that you're responsible for to MD5 hash. And then all you're responsible for is checking a hash. That's a much faster process, and it is a very, very fast update. It makes replication quick, it makes latencies quick between nodes, and it means that by sharing this cache information, even if two nodes are off by 1/10 of a second, we never miss that piece of information. It is rare to vanishingly rare that any two nodes ever visit the same page and catch the same update. And again, even if they do, it doesn't cause any heartache for the rest of the system. And the last one is just don't overthink this stuff. We had a couple different engineers try to go at this problem from a couple different ways. We had people trying to do big graph databases. We had, I think one guy was trying to use TensorFlow. We've had several different attempts to monitor our system because it feels big. But when you think of it like it's just a map, and there's just information in that map, it becomes a really simple problem. You don't need the fancy time series database. You don't really need notifications. You can live with Redis as if it's just a piece of your memory. And when you do that and you realize that simple works, building becomes simpler, and you don't make Redis a problem in your infrastructure. I mean, I've been using Redis, just a small aside, I've been using Redis since 2012 when I used it as a core database on a startup project. I was really surprised when I found out that people thought of Redis as a cache. It was not thought of that way when I originally came across it, so it was very weird to me to come into the new Redis world where it's this sort of side component and it's a cache. I think it's important to remember that at the end of the day, Redis is no different than any other database. It just has a different language that you have to talk to it with. And as soon as you think about it like an in-memory database or a mapped data store, it becomes really easy to think of it as, well, what if it's just a data store that's spread across 100 nodes? I can just run my project on 100 places. I don't have to think about synchrony. And that's part of the beauty of the thing. All right, so it's my end slide, but I'm going to leave up my slides while folks go, or my demo here while folks go out, and we'll ask for some questions if anyone's interested. What can I answer for you? What do you want to know about news?
Okay, I think we have just a moment here of time. So does anybody have any questions for Adam before we get going to break? It's kind of hard to sit between break, but happy to take a question. Oh, we do have questions. Okay, yes, right here.
Unrelated to Redis, how do you display the websites here? Are these iframes?
So these are all iframes. Actually, that's a great question because I'm gonna expand on it a little bit. Part of what we built here, and I think if anybody read the syllabus, you'll see that there are 2 projects mentioned in the syllabus. This was the second one. And what this is a very cool little piece of kit that makes it so that this website can directly read from a Redis database or from a Kafka stream. The actual websites are just iframes, very, very simple page, tiny little piece of JavaScript that's just accepting a Kafka update, flipping the iframe on a page to the new page that comes in, and recording that it saw it in Redis. But it's doing that all from the website. So again, I asked at the beginning, everybody, if you have a website, here's another question. How many of you don't put your Redis data on the web eventually? Because I'll bet the answer to that one's 0. Everything we write eventually goes to a consumer. Most of it goes via the web. This lets you pull it directly to the web without writing a service. And it's sort of a neat little bit of kit that we've been working on.
Was there another question, I think? Yes, no, maybe? Okay, yes? You want to just take that?
How hard is it to maintain? You said when it works at one point, that, when it goes down or when you have to do updates and such, do you have DevOps processes or auto-release processes to keep it up and running?
So originally this was a proof of concept because we were trying to test out Redis and Kafka in our world. So part of the lessons learned here was that if you just leave a Redis cluster in its default state and you do no configuration at all, there are some eccentricities. And it takes a certain amount of DevOps, as you point out, and it takes a certain amount of babysitting to make a Redis cluster really sing. This is what got us involved with Redis Labs, by the way, and why we use Redis Labs in-house, because a lot of it just comes down to needing a certain level of expertise. And maybe it makes sense for most people to invest in dedicated DevOps who know about Redis itself, but for us, that didn't make sense. We're a news company, really. Our digital group facilitates a news use case. So for us, the critical bit was that we invested in a third party that does our hosting, which is to say Redis Labs. We use them to make sure these things stay up. And the production systems that we have running against Redis Labs, I'll admit this demo is not running on Redis Labs because we don't have that much headspace. The production version that we have through Redis Labs doesn't go down. We have very, very high SLAs and SLOs from the hosted solution. What we found out is trying to run it ourselves required more expertise than we thought it would. I mean, to summarize, it's that it isn't perfect by itself. It takes tuning, it takes patience, and we honestly didn't have that patience or institutional wherewithal. So we intentionally had to learn, we intentionally had to investigate this as a way of saying we can't just host this and let it be.
Okay, oh, one more question, and then we do have to take a break. So
I've got 30 seconds left.
Yeah, so you talk about choose Kafka, so why not use the Redis stream as they all talk about. So what's the trade-off you make?
So in this case, it wasn't so much of a trade-off as we were trying to demonstrate both systems. Part of the reason that we didn't use Redis streams for this is that we wanted this information to be durable. The whole point of Kafka is that it is a effectively indefinitely held sequence, and it gives us the kind of partitioning that we were after. It's also write once, so you aren't trying to use it in the particular way, but mostly we did it that way because we were trying to demonstrate the technologies and how they could work together. We were intentionally trying to show that Redis and Kafka were very symbiotic systems. And while you could do all of this just with notifications in Redis, you could do it with Redis streams, you could do it with just update logs, you could do it with time series. There's 100 different ways of modeling the same problem. For us, the critical bit was that we are institutionally invested in Kafka, and we were pushing for us to do a deeper investment in both and show that they had a symbiotic relationship with each other.
Great, thank you.
All right, thank you.